Okay, so on to part 3 of this video. So we're going to do another graphing problem using transformations. So the directions here say to graph f of x equal to -2 times e raised to the x plus 2 power minus 1, and then determine the domain, range, and asymptote. All right, so again, our base function here is e raised to the x power. So graphically, that exponential function contains the point 0, 1, and then 1 comma the base e, which is like 2.7. And then we're just going to perform our transformations in order. So there is a horizontal shift to be performed. So that's going to be the next function that we graph. So e raised to the x plus 2 power is going to shift the previous graph 2 units to the left. So the point that was at 0, 1 is now at -2, 1. And the point that was at 1, 2.7 is now at -1, 2.7. Okay, so graphically our curve is going to look like so. I then am going to multiply that function by 2. So when I multiply that function by 2, the graph gets vertically stretched. So we're going to take each y-coordinate on the graph and multiply the y-coordinate by 2. Okay, so the point that was at -2, 1 is now at -2, 2. And the point that was at 1 comma e, sorry, -1 comma e, which is -1, 2.7, is now going to be at -1, 5.4. Okay, so our 2 points on the graph are going to look like so. We then take the opposite of the entire function. So when I take the opposite of the entire function, that's going to correspond to a y-axis, sorry, an x-axis reflection, which means we're going to take the opposite of the y-coordinates of every point. So the point that was at -2, 2 is now at -2, -2. And the point that was at -1, 5.4 is now at -1, -5.4. Okay, so graphically, our function looks like so. And then the last thing we're going to do is subtract 1. So our function f of x is -2 times e raised to the x plus 2 power minus 1. So when we shift that graph down 1 unit, again, the feature on the graph that we knew was present but we never marked was a horizontal asymptote at y is equal to 0. That now gets shifted to y is equal to -1. And then we're going to take the 2 points on our graph and shift them down 1 unit. So the first point that was at -2, -2 is now at -2, -3. And the point that was at -1, -5.4 is now at -1, -6.4. Okay, so we're going to connect those points like so. Our domain here is all reals. Our range is y is less than -1, so I can write that as the open interval from -infinity to -1. And there is a horizontal asymptote at y is equal to -1. Okay, so those are your examples of graphing with transformations. Let's move on to solving some basic exponential equations. Okay, so there's a rule that we have that we're going to use in this section for solving exponential equations, which states if a raised to the u power is equal to a raised to the v power, then u is equal to v. Okay, so if we can get both sides of our equation written as a single exponential function that shares the same base, then for those two exponential functions to be equal, their powers have to be equal. So u needs to be equal to v. Okay, so with that said, let's do two examples here where the directions ask us to solve the equation. So for number 1, we have 9 raised to the 2x power is equal to 27. Okay, so our goal here when solving this exponential equation is to get both sides of the equation written as an exponent that shares the same base. Okay, and when we look at both sides of the equation, I think a good base choice for both sides is going to be 3, because I can rewrite 9 on the left-hand side as 3 squared, which we are raising to the 2x power. And then on the right-hand side, 27 we can rewrite as 3 cubed. Okay, so I just want to simplify the left-hand side. So we have a power raised to a power. We're going to multiply the exponents. So that makes 3 to the 4x power equal 3 cubed. And now that I have both sides of the equation written as an exponent that shares the same base, for those to be equal, their powers have to be equal. So 4x needs to be equal to 3, which means x needs to be equal to 3 over 4. Okay, I'm going to have you guys try number 2. So for number 2, you have e to the 4th power raised to the x power times e to the x squared power is equal to e raised to the 12th power. All right, so go ahead and pause the video to work through that. And then when you're done, you can unpause and we'll take a look at the solution together. Okay, so with 2, we have e to the 4th power raised to the x power. So when we have a power raised to a power, we're going to multiply the exponents. So that's e to the 4x power times e to the x squared power is equal to e to the 12th power. Again, my goal with this exponential equation is to get both sides of the equation written as a single exponent that shares the same base. So on the left-hand side, when I'm multiplying two exponents that share the same base, I can combine into a single exponent by adding their powers. So we get e to the x squared plus 4x power is equal to e to the 12th power. And now that I have both sides of the equation written as a single exponent, for those to be equal, their powers have to be equal. So x squared plus 4x needs to be equal to 12. And this just turns into a quadratic equation. So I'm going to go ahead and move all the terms to one side and set equal to 0. This is factorable, so it's going to factor to x plus 6 times x minus 2, which means x is equal to negative 6, and x is equal to positive 2. So that equation there has two solutions. Okay, last thing we're going to look at is an application of exponential functions, and we're going to do some more stuff with this at the very end of this unit, but I like introducing this early on. We're going to look at two formulas that we have for compound interest. Okay, so after t years, the balance A in an account with principal P. So when we say principal refers to the initial investment amount, and annual interest rate R. So usually interest rate is expressed with a percentage, but when you plug into these formulas here, you have to write that percentage in decimal form. So again, to go from percent to decimal, you want to move the decimal point 2 spots to the left. Okay, is given by the following formulas. Okay, so the first formula is for in compoundings per year. Okay, so terminology that you will hear for in compoundings per year would be like an account is being compounded annually. So if something's being compounded annually, it's being compounded once per year. Semi-annually is twice per year. Quarterly is 4 times per year. Monthly is 12 times per year. Daily would be 365 times per year. Okay, so If something is being compounded n times per year, the formula that we use to compute the amount A, that's going to be equal to the principal P times the quantity 1 plus the interest rate R divided by n, which is the number of compoundings per year. And then you're going to take that quantity and raise it to the n times t power. Okay, and the second type, or the second formula for compound interest, is for continuous compounding. So that's something that's being compounded infinitely many times. Now, provided that the time is the same and the interest rate is the same and the initial amount is the same, the more times interest gets compounded, the more money you make on that account. So continuous compounding, provided like P and R and T are the same, continuous compounding should make more than n compoundings per year. Okay, so for continuous compounding, our formula is A is equal to P times E raised to the RT power. Okay, so you guys are going to need your calculator for this. It's just one example here with these compound interest formulas. So directions here say that a total of $12,000 is invested at an annual interest rate of 3%. And then we're asked to find the balance after 4 years if the interest is compounded in part A quarterly and in part B continuously. Okay, so I'm going to have you guys work this one out. Make sure you use calculators. We want to round the result here because we're talking about money. We want to round the result to 2 decimal places. Okay, so go ahead and pause the video to work this out. And then when you're done, unpause and you can check your answer against what I came up with. Okay, so for part A, again, our formula is A is equal to P times 1 plus R over N raised to the NT power. So our principal is 12,000 times 1 plus our interest rate is 3%. So as a decimal, that is 0.03. Divided by N, so that's being compounded quarterly, so that's 4 times per year, raised to the N, which is 4, times T, so T is 4 years, so that's going to be 4 times 4 power. And then when we plug that into our calculator, I got A to be approximately $13,523. So $13,523.91. Okay, for part B. So part B says find the balance if interest is compounded continuously. So continuous compounding is A is equal to P times E raised to the RT power. So the amount here is going to be the initial investment, 12,000, times E raised to the R, which is 0.03, times T, which is 4 power. And when we plug that into our calculator, I got A to be approximately $13,529.96. So as I mentioned earlier, if the other variables P, R, and T are the same, which they are in this case, the more frequently that interest is being compounded, the more money you make on your investment. So continuous compounding is getting compounded infinitely many times. That should raise more money than something that is being compounded quarterly in part A. And it does. It winds up making about $6 extra over the course of 4 years. Okay, so that's going to be it. That'll wrap up this lesson on exponential functions. And then we'll start looking at log functions in class on Thursday. Hope you guys have a great rest of your day.